Hello everybody, welcome to Shaders Monthly. Today we talk about mipmaps and how they are used for texture filtering in computer graphics. Furthermore, we will demonstrate the implementation in GLSL. So what are mipmaps? Mipmaps represent a resolution pyramid. At the base level of the pyramid, which we denote as level 0, is the original texture image. Let's assume this image has a resolution of 128 × 128 pixels. Then the next level with index 1 has half the resolution in both directions. In our example, this gives an image of 64 by 64 pixels, 32 by 32, 16 by 16, 8 by 8, 4 by 4, 2 by 2. And at the highest level, the complete image is a single pixel. When we start with 128 × 128 at level 0, the index goes till 7. But when the image resolution of the base level is larger, we get more levels. The total number of levels in addition to the base level is log 2n, where n is the resolution of the base level. The first three letters MIP from the name mipmap refer to the Latin phrase multum in parvo, which translates to much in little. This stresses the fact that mipmaps provide much information in little additional memory space. In fact, the additionally required memory is 1/3 of the memory we need for the input texture on the base level. To provide a visual validation, we mark a red rectangle that has a width of 2/3 of the input texture. If we cut this rectangle in half, the area of the resulting triangle is 1/3 of the original image. Then we move the triangle over here to the images of the mipmap levels and can verify that the data fits perfectly within this triangle. This bit can go here, this one here, and so on. To generate a mipmap level, we need to downsample the previous level by a factor of 2. To this end, we could use different filter operations. In OpenGL, the used filter operation is a very simple one. A pixel value in the new level is the average of 4 pixels from the previous level. In the shown example, we want to go from level 8 by 8 to 4 by 4. For this target pixel, we compute the weighted sum of these 4 pixels to create the average. Each pixel is weighted by a factor of 0.25. The next block of 4 pixels results in the next target pixel, and so on. From a signal processing point of view, using a simple average corresponds to a box filter, which is only a poor low-pass filter, but it is fast to compute. If you are not happy with the mipmap levels that OpenGL generates by default, you can also provide a custom image for each level of the mipmap. The process of downsampling works as described if the resolution of the texture image is a power of 2, for example 128, 256 or 512. For non-power of 2 textures, the filtering operation is more complex. If you're interested in the details, you can find a link in the video description. Because computing mipmaps for non-power of 2 textures is more complex, non-power of 2 textures were not supported in the first versions of OpenGL and WebGL. Why do we need mipmaps for texture mapping? Here you see a camera, and let's assume these small black lines indicate the borders of each pixel in the camera's frame buffer image. The camera is observing a 3D plane, and the texture is applied to this plane. When we move this slider here, we can change the resolution of the texture image. Let's set it to 64 by 64 pixels. To not confuse the pixels of the frame buffer with the pixels of the texture, we call the pixels of the texture texels in the following. So this texture has 64 by 64 texels. To determine the color of this pixel in the frame buffer, we would need to average all these texels which are within the footprint of the pixel. For this example, we would need to take the average of 1, 2, 3, 4, 5, 6, 7, 8 texels. Computing the average at runtime in a shader would be very slow, especially for 2 dimensions on a large texture. Now our mipmap levels come in handy. With this second slider, I can choose the mipmap level. The suitable mipmap level can be computed from the ratio R of texels to pixels. In our example, this ratio is 8 texels per 1 frame buffer pixel. The binary logarithm of this ratio gives us the bitmap level, which is 3 in our case. 1, 2, 3. We see here that the texel of the bitmap level does not cover the footprint of the frame buffer pixel perfectly, but it is a good approximation of the true average. Now OpenGL distinguishes between a magnification and a minification filter. Again, R is a ratio of texels to frame buffer pixels. If this ratio is less than or equal to 1, we have more pixels than texels and the magnification filter is applied. If this ratio is larger than 1, we have more texels than pixels and the minification filter is applied. For the magnification filter there are two choices, nearest and linear. Nearest refers to nearest neighbor interpolation. In this figure, the dashed lines represent the texel grid and the red points are the centers of the texels for which we have a stored color value. In episode number 5, we learned about texture coordinates and that the rasterizer provides us with per pixel texture coordinates in the fragment shader. If we use the texture coordinates to address a 2D location in the texture, this location does not have to be on the texel grid. Instead, it is a floating point 2D vector that can point anywhere. So let's assume the blue point here is a 2D location for which we want to determine a color value. Nearest neighbor interpolation now simply returns the color value of the nearest texel location, which would be this one in our example. The other choice for the magnification filter is linear, which refers to bilinear interpolation. Here's the same setup as before. Again, we want to determine a color value for the location of the blue point. The bilinear interpolation is computed from the color values of the 4 neighboring texels that surround our blue point. The idea of bilinear interpolation is to perform linear interpolations in 2 directions, which are the x and y direction in this example. Thereby it does not matter whether we first interpolate in the x or the y direction. The result is the same. In the shown figure, we first interpolate in x direction using the x position of the blue point within its neighbors. This is done 2 times for the 2 neighbors on top, resulting in a linear interpolated value at this new point, and for the 2 neighbors below, which gives us a result for this new point. Once this is done, we perform linear interpolation in the y direction using the y position of the blue point within the 2 new points. The same thing is now illustrated in 3D. The texel grid is the ground plane and the color values are represented as these red bars that point upwards. The length of the red bars corresponds to the stored color values. Now we first compute the value at location Q1 by linear interpolation. And here's the equation to perform this operation. You see that we use the values at x1, y1 and x2, y1 to perform this operation. Next we compute the value at location Q2 by linear interpolation. The values at x1, y2 and x2, y2 are used. And finally, the linear interpolation in the y direction where the values at Q1 and Q2 are used. Let's talk about the minification filter. We have covered nearest neighbor and bilinear interpolation. We still have to talk about linear mipmap nearest and linear mipmap linear. Linear mipmap nearest means that mipmaps are used and that the used mipmap level is determined by the nearest neighbor. We know that the binary logarithm of the ratio of texels to pixels gives us a suitable mipmap level. Let's assume this value is 1.3. Then the nearest mipmap level would be level 1. And the pixel value would be determined by the bilinear interpolation within level 1. Linear mipmap linear means that mipmaps are used and that the mipmap level drives another linear interpolation. For our example, where the level value is 1.3, this would mean we perform bilinear interpolation in level 1, bilinear interpolation in level 2, and then another linear interpolation dependent on the level value. So for a level value of 1.3, the weighting factor for this value is 0.7 and for this value 0.3 to obtain the final result. Now let's start with the implementation in GLSL. I will use the GSN Composer at gsn-lib.org as a shader editor here, but you can use any other shader editor as well. Links to examples that execute the same shader code using C++ or Java can be found in the video description. Our implementation starts with our example from episode number 5, in which we have applied a texture to a triangle. Click Project and type in the project name Shaders Monthly 05 and click Open Existing. Then open the graph Texture Triangle and press play in the time control panel. Let's replace the triangle with a quad. Click Create and navigate to 3D, Compute, Generate, Plane. Then we connect the Mesh Data node to the Mesh Input slot of the shader node. Perfect, we are rendering a quad that exactly fits the size of the frame buffer. The currently applied texture is this image here. Let's look at the shader code. We select the shader node and click the Edit Code button. This dialog is the shader editor of the GSN Composer. In the top section we can define the vertex shader and in the bottom section the fragment shader. Here we have the uniform variable sampler2d myTexture that represents the input texture. In the fragment shader we use the built-in GLSL texture function to get a color value from the texture. The first parameter is the sampler2d variable and the second parameter is the current texture coordinate. The next line writes the texture color to the frame buffer pixel. We are rendering a full screen quad here and the texture coordinates are in the range from 0 to 1. We can visualize the texture coordinates of the quad by setting the outColor variable to vec4 interpolated text coord.s, interpolated text coord.t 0.0, 1.0. As you see, the red channel goes from 0 to 1 in x direction and the green channel goes from 0 to 1 in y direction. Because our texture coordinates are in the range from 0 to 1 and we are rendering a full screen quad, we get a copy of the input texture as the output of our shader. Let's replace the current texture with another image. Click Create and select Image Processing, Compute, Generate, Shape. This node generates an image that contains a selectable 2D shape. If we connect the Image Data node with the myTexture slot of the shader node, we see that the output of the shader changes. We delete the unused nodes. Next, we select the Shape node and set the size to 32, the width and height of the output image to 64, and the background to white. And we set the displayed shape to square. Now, what is the current ratio of texels to frame buffer pixels? The texture has a size of 64 by 64, and the frame buffer has a size of 1024 to 1024. So the ratio of texels to pixels is 1/16. 1/16 is smaller than 1. Therefore, as we have learned in the slides, the magnification filter is applied. Usually, the magnification filter is selected in the host program, where we would call an OpenGL function. However, in the GSN Composer, you can switch the filter type in the shader code using key value pairs that are placed in a comment after the definition of the sampler2d variable. Uniform sampler2d myTexture magFilter equals linear. Apply code. When we switch between linear and nearest, we see the effect of the magnification filter. For nearest, we get sharp edges. And for linear, we get a linear interpolation, which is mostly visible at the edges of the blue square. If we zoom into the frame buffer for linear, we see that the transition from black to white is a linear gradient. The transition consists of 16 gray levels here because our ratio of texels to pixels is 1/16. If we reduce the frame buffer resolution to 512 × 512, the ratio of texels to pixels is 1/8. Consequently, now the transition from black to white consists of 8 gray levels. Let's load the image from the horse that we know from the slides. It has a resolution of 128 × 128 pixels. A linear magnification filter looks smooth but also a bit blurry. In contrast, Nearest gives sharper results. On the downside, we can observe the staircase effect caused by the individual pixels of the input texture. Let's look into mipmaps and the minification filter. min_filter equals linear_mipmap_nearest. This changes nothing because currently the ratio of texels to pixels is smaller than 1 and the magnification filter is used. However, when we use the built-in GLSL function texture_LOD, where LOD is short for level of detail, we can enforce the usage of a certain mipmap level. Texture_LOD myTexture interpolated text coord level. Let's expose the level as a uniform variable, uniform float level. Apply and close. If we increase the level, you see that the used mipmap levels are changing in discrete steps and the details are disappearing. As expected, when we reach a mipmap level of 7, we get a single uniform color, which is the average of the input texture. Let's go back to level 4. At level 4, the resolution of the mipmap level is 8 by 8 pixels if the input resolution is 128 × 128. However, in our result, we do not see the individual pixels, but a bilinear interpolation. This is the expected result, because the filter setting linear mipmap nearest means we use the nearest mipmap level, but within the level a bilinear interpolation is performed. If we want to see the individual pixels of the underlying mipmap level, we can clone the shader node, connect the inputs, and set the frame buffer resolution to 8 by 8 pixels. If we compare the two outputs, we can clearly see their relation. The center of this bright pixel is here, and the center of this dark pixel is here. Let's change the minification filter to linear mipmap linear. Apply and close. If we change the level, you see that the used mipmap levels are no longer changing in discrete steps, but continuously. As we know from the slides, this is achieved by a trilinear interpolation. Until now, we have changed the mipmap levels manually using the texture_LOD function. Next, we have a look at an example where the levels are selected automatically using the regular texture GLSL function. We open the graph textured cube from the last episode. Here you see a rotating textured cube. The fragment shader is the same as before, but uses the regular texture GLSL function. We replace the cube with a plane. 3D compute generate plane. Then we scale the size of the plane by a factor of 10. We change the resolution of the texture to 2048 × 2048 and the resolution of the frame buffer to 512 × 512. These changes make it more likely that the ratio of texels and pixels is larger than 1 and the minification filter is applied. We open the shader editor again and change the minification filter to nearest. min_filter equals nearest. Apply code. Now we see in the shader output that nearest neighbor interpolation produces aliasing and noise. This is because it is kind of random which texel is hit by the texture lookup when there are many texels per frame buffer pixel. If we change the filter to linear, this does not improve the result significantly. However, when we change to linear_midmap_nearest, this removes the noise. The other possible setting is linear_midmap_linear, which works as well. However, the visual difference is very small here. To visualize the difference, I have prepared an example which you can find in the project Shaders Monthly 06. The graph's name is Midmaps. This is the same setup that we have just created, but additionally I have added a special midmap with custom level images. In this special midmap, each midmap level has a different color. If we connect the midmap texture to the shader, we see a color coding of the selected midmap level. This is the output for linear_midmap_nearest. If we change the filter to linear_midmap_linear, we see the result of the linear midmap level interpolation. Okay, that's it for today. If you have questions, use the comments or get in contact with me. As always, if you prefer C++ or Java source code, this can be exported in the shader editor of the GSN Composer or can be found in the video description. See you at the next episode of Shaders Monthly.